Hi, imagine you're a used car salesman. You've sold many cars and have collected data on all the past sales. And now you're hoping to predict the selling price of a car based on some of its characteristics. To predict the selling price Y of a car, we use two main factors: the car's age, denoted by X1, and the engine size, that will be X2. These characteristics, known as predictors, will help us estimate the price. Using linear regression, we model the relationship between the predictors and price with the formula y equals beta 0 plus beta 1 times x1 plus beta 2 times x2 plus u. And here u is an error term with mean 0. Now these parameters, beta 0 and beta 1 and beta 2, are estimated using the least squares method, which finds the best fitting formula by minimizing the squared differences between actual and predicted prices. Data is organized into a design matrix X, allowing us to calculate these parameter estimates. The least squares estimates for our parameters can be found with the formula that you see on the screen. Okay, now that we have estimates for beta 0, beta 1 and beta 2, the next question is whether these estimates are unbiased. An estimator is unbiased if on average it equals the true value of the parameter we're trying to estimate. Now, to show that our estimates are unbiased, we look at the expected value of the estimator vector. First, we plug in the estimators obtained by the least squares method. And now, because the x values are considered to be constant, we can take them outside of the expectation. And therefore, we find that this expected value is indeed equal to the true parameter vector. So this confirms that our estimators for beta 0, beta 1 and beta 2 are unbiased, and meaning they each estimate the true value on average. In the final step of our analysis, we want to set up confidence intervals for our parameter estimates. A confidence interval gives a range within which we expect the true parameter values to lie, with a certain level of confidence at, for example, 95%. Now, to construct these intervals, we would like to know about the typical error that we are making on the beta. Mathematically, beta hat is a random variable, since it depends on our data, which are realizations of random variables. This means that we want to know the standard deviation of beta hat. Now, the noisier our data is, the harder it is to estimate our beta. This means that the standard deviation of beta hat is proportional to the standard deviation of the error u, which we will call sigma. The proportionality constant happens to be the square root of the ith diagonal element from the inverse of the matrix x transpose times x. There's one problem, and that is that I don't know this standard deviation of the noise. Luckily, there is a solution. I first estimate the standard deviation of the noise, sigma, by sigma hat. In this way, I get an estimate of the standard deviation of beta hat. This is called the standard error of beta hat, denoted by SE. It tells you how uncertain our estimate of beta hat actually is. Okay, if the errors are normally distributed, then we can show that the difference between each beta and its estimator divided by the standard error follows a t-distribution with n-3 degrees of freedom. And this is great news. We finally know the distribution of the beta parameter that we are interested in. This t-distribution allows us to construct the confidence intervals for each parameter. So, for a given significance level, like alpha equals 0.05 for a 95 confidence interval, we use the critical value from the t-distribution to calculate each interval. This process gives us a range of values within which we are confident the true parameter lies. Okay, let's revisit our used car dataset. By using some software, such as Python for example, we can calculate confidence intervals for our regression parameters. In this example, we've estimated the coefficients and calculated the 95% confidence intervals. In the bottom left corner of the screen, you will see that the estimate for beta 1 is approximately minus 1828. This value tells us that for every additional year of the car's age, the price decreases by about 1,800 euros, on average, assuming that all else remains equal. The next column is this famous standard error, the uncertainty of our estimates. This tells us that the uncertainty about that minus 1828 is plus or minus 15. Then in the bottom right corner, we see the confidence intervals for each parameter. For example, the 95% confidence interval for beta 2, which corresponds to the engine size, ranges from 4,692 to 5,017. This means that with 95% confidence, we can say that the true value of beta 2 lies somewhere between those two numbers. Now, imagine for a moment that this confidence interval included the number 0. If that were the case, we wouldn't be able to say with 95% confidence that engine size has any effect on the car's price. A confidence interval that contains 0 indicates that the relationship is not statistically significant at the 95% confidence level. Okay, and that's a wrap. You now have a foundational understanding of how we estimate parameters and construct confidence intervals in a regression model. Thank you for following along, and I will see you in the next lecture.